Hi, I'm on the JOIDUS Resolution again, and this time we're just offshore from the Great Barrier Reef in Australia. This is the Coral Sea, ODP leg 194. The goal of this leg is to reconstruct the magnitude of Miocene sea level. So it's one of many ODP IODP expedition that relies on the principle of sequence stratigraphy to try to understand our natural world and the past Earth's condition better. So let's talk about sequence stratigraphy. So in our first lecture, we talked about unconformity. And in a second lecture, we looked at chronostratigraphy. And we've also talked about the fact that lithostratigraphic units are not chronostratigraphic units. In this important lecture, I will introduce the concept of sequence stratigraphy, which is a modern way to look at sediments in space and time. Now, in a nutshell, sequence stratigraphy is the science of looking at genetically related. So I think that the best way to understand sequence stratigraphy is to take a historical trip down stratigraphy and how different notions came into being and how in the late 70s these were assembled into the science of sequence stratigraphy that we know today. And perhaps one of the first pioneer in that way of thinking was Walter, a German stratigrapher who came up with Walter's law. Now, Walter's law is essentially to recognize that the stratigraphic record is subdivided by conformable and unconformable surfaces. And Walter's law states that to be conformable, a succession needs to have a juxtaposition of facies vertically in a log that is similar to the juxtaposition of facies you would find laterally in the depositional environment. So effectively, Walter's law reflects on the sediments in space and in time. So in this diagram, what you see is a vertical log with three facies, the upper shore face, middle shore face, and the lower shore face. And then we also have a sense of the lateral distribution of those facies. And Walter's law stipulates that to be conformable, the vertical succession of facies must also correspond to the lateral succession of facies. So, for instance, if we start with the lower shore face at the base of this section, on top of this we expect the middle shore face, and on top of that we expect the upper shore face. And if that is the case, then we most likely are looking at a conformable succession of facies. So in concrete terms, what does that mean for environment of deposition and what we can expect to find in the stratigraphic record? So here's an example where we have a beach facies, which is sand, followed by silt, which is a finer facies, followed by clay, much deeper in the depositional environment, and finally deep in the basin we find carbonate mud. Now, a conformable succession would show the same succession of facies. That means that a timeline would basically follow this dashed red line. So you can see then that it's very obvious if this red line is if this dashed red line is a timeline, then lithostratigraphy, the units that represent one lithology, are not chronostratigraphic units. So lithofacies are time transgressive. That's one very important conclusion you can get from Walter's law. It's also obvious that what we see here is a shift in the position of facies. At first, in blue, we have a transgression. That's when base level, I will use the term base level, which is essentially equates to sea level, and for simplification, when base level rises or sea level rises, the facies then migrates towards the continent, and that's a transgression, and this is followed by a regression, and that's a very big concept in sequence stratigraphy that we will explore how and why we have transgression, regression cycles. So if Walter's law is the first step in trying to understand sequence stratigraphy, The second step, a very important step, is the notion that a surface, an erosional surface, can be a time surface, because that's one of the tenets of sequence stratigraphy. And the first researcher to actually use stratigraphic surfaces as timeline is Elliot Blackwelder in 1909, where he published the use of unconformities as time markers. So if you look at this figure, what he noticed is that the sediments that are folded at the base, we don't really know when they were deposited. It's very hard to find a surface in those sediments that represents a timeline. Same thing for the sediments that are unconformably overlying this sequence. However, the unconformity itself, marked here by the red arrow, that unconformity represents a timeline. This is the timeline when essentially we had erosion of the folded sediments.